Hello friends, welcome back in this video session of heat transfer subject. In today's video lecture, we will cover boiling and condensation. My name is Mr. S.V. Kumbar, Assistant Professor, Sharad Institute of Technology, College of Engineering, Yadra, Ichalkaranchi. So these are the contents of today's video lecture. First, introduction to boiling. Next, application of boiling and condensation, boiling processes and its types, pool boiling regimes, and forced convection boiling, which will be related to internal flow. So we'll start with introduction. So I would like to ask one question to you. Have you seen boiling anywhere? For that, boiling process or condensation process of heat transfer involves phase change, that is from solid to liquid or from liquid to gaseous, right? So such processes are very complex than simple exchange between fluids. Up till now we have studied conduction, convection, where simple heat exchange took place, but here it usually involves heat changes at constant or nearly constant temperature. That's why it is somewhat complex than conduction or convection, or you can say simple heat transfer problem. So when a vapor is exposed to a surface at a temperature below saturation temperature, then condensation in the form of liquid film or individual droplet occurs on the surface. Heat transfer from condensing vapor. Condensation of vapors on tube surface is cooler than condensing temperature of vapor. Those such as water, hydrocarbon and volatile substances that are processed where latent heat of vaporization is removed for the condensation to occur. And condensing vapor consists of single substance or a mixture of condensable and non-condensable gases or a mixture of all. Application of boiling and condensation. So first application is very familiar to us, refrigeration and air conditioning. In domestic refrigerator, we generally use condenser and evaporator. You had seen condenser in the form of coil, which is at back side of domestic refrigerator, and evaporator is the part where cooling effect is achieved. So in both condenser as well as evaporator, boiling and condensation phenomenon is observed. Melting of metal in furnace. When heat is supplied to any metal, it will be converted into liquid. So this phenomenon is applicable to boiling and condensation. Steam power plants. Boilers and condenser is the best example, where in boiler heat is supplied to water which is flowing through tube and it will be converted into vapor. And in the condenser, after expansion of this steam in turbine, it is condensed. It is converted into vapor to liquid. In sugar mills and refineries, we use heat exchanger to transfer heat from hot fluid to cold fluid. Process heating and cooling. Cooling of nuclear reactor and motor. So boiling. So have you seen boiling anywhere? Yes, you have seen boiling in kitchen. If you take water in utensil or pot and if you supply heat energy, that water will be boiled, right? So what does boiling mean? Boiling is the convective heat transfer process that involves a phase change from liquid to vapor state, right? Just as I said few minutes back, if you supply heat energy to any liquid, it will be converted into vapor, right? And here heat will be supplied to the liquid which is in the container through the interface between solid and liquid. So interface means this liquid is in contact with pot. That's why boiling can also be defined as evaporation at solid liquid surface, and this is possible only when the temperature of surface, that is surface temperature of this pot, exceeds saturation temperature of corresponding liquid, that is Tsat. And heat transferred to solid surface to liquid surface according to the law Q is equal to HA Ts minus Tsat, where H is the convective heat transfer coefficient, A is the surface area of that pot at bottom, Ts is the surface temperature of surface, Tsat is the saturation temperature of liquid, and Ts minus Tsat is nothing but excess temperature. An application of boiling heat transfer, first application is very common, steam production in steam and nuclear power plant, that is thermal power plant, where heat energy is used to convert water into steam. Second, distillation of refineries of liquid, concentration, dehydration and drying of foods and material, heat absorption in refrigeration and air conditioning system. These are some applications of boiling heat transfer. Now, types of boiling. There are basically 4 types of boiling. First one, pool boiling. In pool boiling, liquid is heated with the help of a surface, and that heat is applied to the liquid, and heat is transferred within liquid by free convection only. So that boiling is known as pool boiling. And pool boiling generally occurs in steam boilers, which involves natural convection. Second type of boiling is forced convection boiling, where the fluid will be in flowing condition. The liquid which is in the tube will be in flowing condition, and for that purpose we require external agency, that is pump. That's why it is known as forced convection boiling, which occurs in water tube boiler. Third type of boiling is subcooled boiling or local boiling, where the liquid temperature is below the saturation temperature and bubbles are formed in the vicinity of heat surface, and these bubbles, after traveling a short path, get condensed in the liquid itself, which has a temperature less than boiling point. Fourth type of boiling is saturated boiling, where the liquid temperature exceeds saturation temperature. The bubbles formed at solid surface are then propelled through the liquid by buoyancy effect. Now we will see pool boiling regimes. The process of boiling depends upon the nature of surface, thermophysical properties of the fluid and vapor bubble dynamics. So there are so many variables, that's why we can't use general equation. For that purpose we will consider one figure. So in this figure, a liquid is taken in container, solid is nothing but liquid solid interface, and when heat is supplied to this liquid, heat will be transferred within the liquid by the free convection, and because of free convection liquid is heated, and after its saturation temperature bubbles are formed, and it is evident from the graph where there is a sharp decline in the liquid temperature close to the solid surface. The temperature through most of the liquid remains slightly above the saturation, but consequently bubbles generated at liquid solid interface rise to the and transported across the liquid vapor interface. Whether the boiling corresponding to pool boiling or forced boiling, now there are 3 regimes, we will see one by one later on: interface evaporation, nucleate boiling and film boiling. For that purpose, student may imagine one example. Have you seen electrical water heater in the form of coil? If you place electrical water heater in water and if electrical current is start, so what will happen? After some time that liquid gets boiled. Another example I would like to mention here: if an electrically heated platinum wire is submerged in a pool of water by varying its surface temperature, and when heat flux, that is Q upon A, heat transfer per unit area, is measured, so we can draw boiling regimes, pool boiling regimes. So pool boiling regimes, so I was talking about this diagram. So if you plot heat flux, that is Qs in watt per meter square versus excess temperature Ts minus Tsat, we will find there are 3 different regimes. First one, interface or evaporation. Second, nucleate boiling, and third, film boiling. Now imagine one example that I mentioned earlier, that is, if an electrical coil is kept in water, and when electrical current is started, that liquid will start boiling. So as the excess temperature, that is surface temperature minus saturation temperature of that liquid, goes to 5 degrees centigrade, which is nearly equal to 5 degrees centigrade, so interface evaporation or free convection pool boiling regime is observed. So in this regime, heat will be supplied to liquid, and that liquid flows by convection current. You might have seen while preparation of tea or coffee, that liquid circulates, that is known as free convection. So here heat is transferred by the superheated liquid rising to liquid vapor interface where evaporation takes place. So with further increase in excess temperature, so bubble formation starts, and that regime is nothing but nucleate boiling. Nucleate boiling is characteristic by bubble formation. So again there are two sub regimes, that is in first bubble condenses in superheated liquid, and the second phase bubble rises to the surface and it will reach to the free surface of liquid. So this is nothing but nucleate boiling, and nucleate boiling generally occurs when the excess temperature is above 50 degrees centigrade. So there is a one point where maximum heat flux occurs. That point is known as critical heat flux or burnout point, where there is a maximum heat flux, and this is the point where transition from nucleate boiling to film boiling starts. So as excess temperature further rises, heat flux decreases rapidly, and it is the initiation of film boiling, right? So in film boiling, that coil is covered with a thin film of the liquid, and there are three sub regions. That is, first one is the unstable film. The film is still not stable with further increase in excess temperature. After the temperature within 50 to 150 degrees centigrade, excess temperature 50 to 150 degrees centigrade, the film becomes stable, and with further increase in excess temperature, radiation comes into play, means that heater coil and water is completely isolated by film boiling, and there may be chances of failure of that heater at B point. So this is all about pool boiling regimes. So this is the explanation of pool boiling regimes. First, interface evaporation. As I mentioned here, when the temperature difference is nearly about 5 degrees centigrade, in this region liquid near to the surface is superheated slightly, and the convection current circulates the liquid, and evaporation takes place at the liquid surface. Second type of nucleate boiling, which is the characterization of bubble formation. And next, film boiling, where the temperature difference is 50 degrees centigrade to 150 degrees centigrade. These conditions oscillate between nucleate and film boiling, right? Critical heat flux that we have studied. The critical heat flux is the point of maximum heat flux on the boiling curve at which transition from nucleate to boiling, film boiling initiates. This point is also called as boiling crisis, because the boiling process beyond this point, normally the melting of solid. I was talking about that metal, that is electrical heating coil. So the heating of metallic surface is not limited to a point A, but it is possible that the metal may get damaged, or it may even melt inside water, right? That's why it is also known as crisis, burnout point or critical crisis. Next one is forced convection boiling, which will be related to internal flow. In many mechanical engineering applications, the liquid flows through a tube and it may be heated or cooled. Best example is refrigeration and air conditioning, as well as in thermal power plant, right? In case of refrigeration and air conditioning, a refrigerant flows through tube and it is heated or it is cooled in condenser or evaporator. When this high temperature, high pressure vapor flows through condenser, a cooling fluid flows through this, and because of which it is converted into high pressure, low temperature liquid. Phase change takes place in condenser when it is flowing through tube. It is nothing but forced convection boiling. It is an example of forced convection boiling. Similar thing happens in case of evaporator, where this low temperature, low pressure liquid refrigerant flows through evaporator, and the object which is to be cooled is put in evaporator coil. Here it takes heat energy from the object which is to be cooled and it is converted into vapor. Similarly, in case of boiler, when water is heated inside the water tube boiler, say Babcock and Wilcox boiler, what will happen? When as the water flows through the tube, it will be converted into vapor. So it is the example of forced convection boiling. Now in forced convection boiling, that is when we use term boiler, condenser, steam generator or evaporator, we usually refer to equipment that involves heat transfer within tube. The prediction of heat transfer coefficient in the system is often essential to determine overall heat transfer coefficient U and sizing the equipment. Now we will see forced convection boiling, that is related to internal flow. Now consider this tube through which liquid is flowing in upward direction, right? Now there are temperature variation, flow pattern variation and heat transfer region which are shown in this image. So consider a tube through which liquid is flowing in upward direction. Now as this liquid is heated, when it moves from lower position to top position, first of all, as it is a single phase liquid, it will be converted into bubbly flow. Bubbles formation starts in the next phase as heat is applied. Further increase in temperature, there is annular flow. Next, slug flow, annular flow with entertainment, and last one is the drop flow, right? And if you talk about heat transfer region, first region is convective heat transfer to liquid. Second region in the bubbly flow, subcooled boiling. In the annular flow, it is saturated nucleate boiling. In the next, forced convection heat transfer through liquid film. And last one is the liquid deficient region, right? So this is the transfer of heat or conversion of liquid into vapor in case of forced convection boiling. And if you observe the temperature variation, here somewhat the temperature of liquid is shown as well as wall temperature of this tube is also shown. So the wall temperature as well as liquid temperature increases suddenly after dry out point, means when it is converted to vapor, it is quickly converted, or the temperature is quickly rises, and finally that vapor can be used for the final application, right? And the applications of forced convection boiling are that we had studied earlier, that is first one refrigeration and air conditioning, condenser and evaporator of refrigerant. Second, thermal power plant, both steam as well as nuclear power plant, where steam is produced with the help of heat energy and that steam can be used for the further application, right? So for this moment we will stop here. Thank you very much.